The last month was a blur of hope and then a sudden brutal crash. Starship Flight 9. It was so agonizingly close. It soared, majestic, a silver spear aimed at the heavens. The mission aimed for orbit, a test of its ultimate destiny. It carried dummy satellites ready for deployment. A controlled splashdown in the vast Indian Ocean was the final, triumphant act. Then, in an instant, everything changed. A silent enemy emerged from within the beast itself. The spacecraft suddenly suffered a fuel leak. The leak became a gash. Pressure plummeted. Control was lost. The crucial payload bay door, vital for its mission, simply failed to open. The vehicle, once so promising, was destroyed mid-air. It was a rapid, unscheduled disassembly, a stark reminder of the immense challenges we face beyond our fragile blue planet. Despite the crushing disappointment, the engineers at SpaceX wasted no time. They are relentless. Within days, sometimes hours, they had identified the root causes. They dissected the telemetry, sifting through millions of data points, searching for the fatal flaw. They rolled out solid fixes. These were not minor tweaks. They were significant, targeted upgrades. All of this aimed at one goal, to make absolutely sure Flight 10 would finally make history. This month. So what exactly did they change? What desperate, brilliant modifications did they implement to ensure this behemoth finally reaches low Earth orbit, and stays there, this time? Let's break down this incredible race against time right now. Starship Flight 10 is currently poised for launch. The clock is ticking. It is scheduled to launch at the very end of this month, a mere 10 to 15 days away. It is an incredibly tight deadline, a testament to SpaceX's almost obsessive pursuit of speed. To meet that deadline, every team member, every engineer, every technician is racing against the clock. They are battling time itself, ensuring every component, every system, is perfectly aligned. They work without pause, driven by an unyielding ambition. This is not just a test, it is a desperate sprint towards a future we desperately need. Ship 36, the specific vehicle assigned to this critical mission, has already made astonishing progress. The sheer pace of development is mind-boggling. Just recently, on June 15th, it was precisely mounted on the static fire stand. Then it was carefully, slowly rolled out to the Massey test site, its massive frame gleaming under the Texas sun. A mere day later, it underwent successful cryo-loading, its tanks filled with super-chilled propellants. The massive aft flaps, crucial for re-entry control, were rigorously tested. It then completed a single-engine static fire, a critical precursor to full power. A full 6-engine static fire test is expected soon, a truly terrifying display of raw power, before the ship is rolled back to the Mega Bay 2 for its final, painstaking preparations. Meanwhile, Booster 16, the colossal first stage that will hurl Starship skyward, is more ready than ever. Its sheer power is almost incomprehensible. It recently completed a full-duration static fire. All 33 Raptor 2 engines roared to life, unleashing an incredible inferno for 20 full seconds. The raw power, the sheer earth-shaking thrust it unleashed, was just incredible. It defied belief. Notably, Booster 16's hot staging ring, a crucial component for the daring mid-air stage separation maneuver, has been moved into Mega Bay 1. This is for immediate installation. This prepares it fully for Starship Test Flight 10, a mission pregnant with anticipation. Many in the spaceflight community hold a deep belief. They whisper that Booster 16 could be the very last Block 2 booster to ever attempt a Mechazilla catch. This is that daring maneuver where the giant robotic arms of the launch tower grab the descending booster right out of the sky. It is a moment of breathtaking precision. But either way, whether it is caught or makes a controlled splashdown, we will still get to witness this unforgettable moment once again. This is something we tragically didn't get to see during Flight 9, since that mission was instead focused on testing the reusability of Booster 14. That was a different but equally vital test. On this upcoming flight, SpaceX's top priority is absolute clarity. They need to verify without a shadow of a doubt whether the numerous upgrades made to Ship 36 are actually doing their job. Will they hold up under the immense stresses of launch in space? Or will some of the old, insidious issues from Ship 35, the previous iteration, subtly creep back in? Every sensor will be scrutinized. Every data point will be analyzed. This is a scientific mission wrapped in a dramatic flight test. The stakes are immense, but the lessons learned are invaluable for every future flight. But this mission isn't just about fixing past problems. That is only part of the equation. The ultimate, overarching goal is still grander: to finally get Starship to orbit, to prove that it can not only survive the brutal ascent but also function flawlessly once it's up there. To achieve that, SpaceX will not only test the Starlink deployment system, deploying a new batch of dummy satellites. They will also attempt a number of critical in-flight maneuvers. Each one is a step towards true interplanetary capability. The future of Starship hinges on their success. One of the most challenging of these maneuvers is restarting a Raptor engine in the vacuum of space. This is not the headline goal, not the one that grabs the front page, but it is an absolutely essential step. It is critical in validating Starship's ability to operate in orbit, to perform orbital transfers, and ultimately to make it to Mars. Flight 9 couldn't even get that far. It barely had a chance to attempt such complex operations. That failure was mostly because of a major propellant leak, a devastating internal wound that caused a rapid pressure drop and shut down the engines prematurely. So, to truly understand how SpaceX is working to fix that, how they are building a path to success, we need to rewind a bit. We need to look deeply at what truly went wrong during Flight 9. Of all the challenges faced during Flight 9, the most critical, the most devastating one, was undoubtedly a propellant leak. Elon Musk himself confirmed the grim reality. He stated clearly that the leak happened inside the main tank, an unexpected rupture. This internal bleeding caused pressure inside the tank to drop rapidly, dangerously. And that critical drop in pressure ultimately ended up starving the engines of their vital fuel. It was a slow, agonizing death for the mission, cutting it short, preventing Starship from completing its key tests in orbit. This wasn't just a momentary glitch, a fleeting issue that could be ignored. The leak actually started early in the flight, well before the payload deployment phase was even supposed to begin. It was a ticking time bomb. As a direct result of that unseen leak, one of the engines began losing thrust. Its power output dwindled, a clear sign of distress. This happened right before the second engine dramatically shut down. That's when things started to go sideways, quite literally. The initial deviation was subtle, almost imperceptible. But it quickly became more obvious, chillingly so, when the onboard camera switched to the payload bay. What it showed was a nightmare in progress. Tiny frost particles could be seen drifting steadily in one direction, a clear, unmistakable sign. The entire ship had started spinning out of control. It was a slow, majestic, yet terrifying death spiral. In situations like this, regaining control is always the top, absolute priority. It is the immediate, desperate imperative. Normally, the first tactical move would be to restart the engines. The plan would be to then use the 3 powerful vacuum Raptors to steer and stabilize the vehicle. They would act as giant thrusters, forcing the ship back into its intended orientation. But this time, that simply wasn't an option. The insidious fuel leak had already fatally compromised engine performance. It had stolen their lifeblood. This made any restart attempt, no matter how desperate, impossible. The vehicle was adrift. Instead, in a desperate gamble, SpaceX turned to its backup system. This was the cold gas thruster system, or more precisely, the gaseous oxygen and nitrogen cold gas thruster system, used for attitude control. This technique relies on gas pressure generated by heated propellant vapor. This pressure is designed to help push liquid fuel toward the engines and to precisely guide the ship's orientation in space. It is a brilliant piece of backup engineering, a last resort. But there's a catch, a cruel twist of fate. It only works if the internal tank pressure remains stable. And once again, the relentless leak undermined that system too. With pressure continuing to drop, even the backup control method failed. All recovery efforts became tragically ineffective. The mission was ultimately doomed, a victim of a single compounding flaw. It's a textbook example of how a single, seemingly isolated leak can cascade into total system failure. It can shut down engines. It can disable critical control systems. It can eventually compromise the entire vehicle, leading to its destruction. The elegance of the design is matched only by its fragility. So, how exactly is SpaceX planning to solve this persistent leak issue? As we've discussed before, it's a seriously complex challenge, especially when dealing with supercooled propellants in the extreme and unpredictable environment of space. It requires ingenuity, precision, and an almost obsessive attention to detail. The first, immediate priority is to reduce both the likelihood and, crucially, the impact of any potential leaks. Prevention is paramount. One practical approach, already being implemented, is reinforcing vulnerable components. This includes the intricate fuel tanks themselves, the complex manifolds, and the critical plumbing that carries the volatile propellants. They are adding protective layers. They are integrating structural dampers. These sophisticated additions can help absorb the intense vibrations that rockets experience during launch and flight, vibrations that can create minute cracks and prevent leaks from forming in the first place. It is a silent battle against unseen forces. Another innovative idea being actively considered, a truly futuristic solution, is an automated sealing system. Imagine a system capable of detecting a leak the very moment it happens, no matter how small, and then sealing it off immediately. It would be an almost biological response, a self-healing spacecraft. Of course, developing something that precise, that responsive, is no small feat. It pushes the boundaries of material science and autonomous systems. But if SpaceX can pull it off, if they can make this visionary system a reality, it could greatly increase Starship's reliability throughout the entire flight. It would be a game changer, a profound leap forward in space safety. That's the prevention side, the immediate fixes to existing weaknesses. But to truly fix the root of the problem, to address the core vulnerability, SpaceX also needs to improve how Starship is actually built. This means starting with more advanced weld inspection techniques. It means embracing cutting-edge technology to see what the human eye cannot. This includes non-destructive testing, or NDT. This is a method that catches internal flaws, things like microscopic cracks, porosity, slag inclusions, delamination, or incomplete fusion, before they can ever lead to catastrophic failure. It is like an X-ray vision for steel. And when it comes to those welds, especially in the massive super-cold fuel tanks, quality is absolutely everything. The slightest imperfection, a microscopic void, can become a major weakness under the immense stresses of launch and flight. Right now, many of those critical welds are still done manually, using a modified TIG welding process. It's effective, yes, but it remains vulnerable to human error. Even the smallest imperfection, a barely visible flaw, could turn into a major weakness under the unforgiving high stress of a launch. That's why switching to high-precision methods like advanced laser welding or electron beam welding could be a revolutionary leap. These advanced techniques, laser welding or electron beam welding, are game changers. They deliver much tighter control over the welding process. They minimize the heat-affected zones, preventing microscopic weaknesses from forming. Crucially, they produce stronger, far more consistent welds. This is exactly what's needed to handle the intense vibration Starship faces during its thunderous launch and the violent buffet of atmospheric flight. So what do you think? If you've got a creative idea for fixing Starship's leak issues, something truly out of the box, drop it down in the comments. We'd love to hear your take. By the way, we're getting close to 150,000 subscribers, and your support means the world to us. It truly keeps us motivated to bring you even better videos every single day. Thank you so much for being part of this journey. Alright, now let's move on to the next problem, one that seemed relatively minor but could derail an entire mission: the Starlink deployment system. A lot of people have been wondering about the PZ payload door. Why did it only open partway on Ship 35 during Flight 9? It seemed perplexing. After all, SpaceX had already tested it successfully on the ground before launch. They even loaded 8 dummy Starlink satellites inside the door. Everything seemed to work fine, flawlessly even. But opening a large cargo door in the vacuum of space, under extreme temperature fluctuations, is a whole different beast. It is a challenge that reveals the brutal, unforgiving nature of space itself. Many experts constantly point out that doors in space are incredibly tricky. They are deceptively complex. These mechanisms have to operate reliably, time and time again, without compromising the vehicle's structural integrity. All this, while surviving the most extreme conditions imaginable in orbit. We're talking temperatures that can soar as high as 2,600 degrees Fahrenheit during re-entry, when the ship slams into the atmosphere at nearly 28,000 kilometers per hour. And then, it plunges to as low as minus 454 degrees Fahrenheit when it's in the chilling shadow of Earth. That kind of thermal swing from searing heat to absolute frigidity causes materials to expand and contract drastically. This brutal cycling can easily interfere with even the most precisely engineered moving parts. And here's something that's incredibly easy to overlook, something subtle yet profound. Materials don't behave the same way in space as they do on Earth. Gravity, or the lack thereof, changes everything. A large metal structure, meticulously assembled under Earth's constant gravitational pull, can subtly shift once it's in the weightless environment of orbit. Parts that had tiny, almost invisible gaps between them on Earth might press tightly together in microgravity. That subtle shift could be enough to jam a mechanism if it's not perfectly engineered for the unforgiving environment. There's also the chilling possibility that leaking propellant, that insidious killer from earlier, found its way into the payload bay. That could have altered the internal pressure balance or even created mechanical resistance, making it harder for the door to function. Just imagine the sheer gut-wrenching disaster if Ship 36 makes it all the way to orbit, survives the journey, only to fail at deploying the Starlink satellites. That would be a catastrophic waste of time, money, and monumental effort. To prevent this nightmare scenario from ever happening again, SpaceX is taking radical steps. They might need to significantly upgrade the PZ door's thermal protection. This is not a simple matter of thicker insulation. Using advanced materials like aerogel or thermal ceramic composites to shield sensitive mechanical parts could make a monumental difference. These revolutionary materials can handle extreme temperatures, ranging from a bone-chilling -390 degrees Fahrenheit to over 2,800 degrees Fahrenheit, a truly astonishing range. This protects the door's moving components from warping or locking up due to those brutal thermal expansions and contractions. It's about building a shield against the fury of space. Another smart move, a testament to their meticulous design philosophy, would be to add expansion gaps directly into the door structure itself. These are small, precisely engineered clearances that allow the metal to expand and contract without binding, while still maintaining critical internal pressure. It's a subtle yet vital design feature. And just in case the main actuators, the primary motors that open the door, tragically fail, SpaceX could also include a backup system. Perhaps a manual or even a semi-automatic pneumatic piston, completely independent from the main electronics. If the primary motor doesn't respond, if it jams or fails, this backup could kick in, forcing the door open and finishing the job. That's the kind of fail-safe engineering, the redundancy, needed to make sure the PZ door operates reliably, no matter what space throws at it.